Hello everyone, welcome to my channel, and this is an educational channel. We focus on learning about theories of everything and going in depth and seeing what they can do for us. Today is our 500th video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson put together his reciprocal system of theory over the years of the middle 20th century. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And from there, he derived a theoretical universe, what his universe would look like if his postulates were correct. And then over the course of the last 30 years of his life, he wrote books where he compared his theoretical universe with the actual empirical measured universe of the legacy scientists. And we are looking at one of those products right now. Here, his 1987 book, Basic Properties of Matter, which is on chemistry. We're in chapter 16 of that book today, called Induction of Charges. Now, if you would like to go deeper into the reciprocal system and figure out the ins and outs, the fundamental postulates, and how they operate, you're going to want to watch one of my first 474 videos on this subject, where I go into that in at least some level of depth and, enough to kind of be able to follow along. Today, we're going to just be reading from this book, and I might make some parenthetical comments, but, we're going to try to cover some ground here. So I'm going to basically assume that you have some type of knowledge or understanding of the reciprocal system, and or you are an intrepid, explorer into the unknown, and you're willing to just wing it and listen to what Larson has to say without having any, foundational background in what he's talking about. Either way, but go to one of my first 474 videos if you'd like to get up to speed. Okay, we're going to start right here. The locations occupied by the charges in any charged conducting object not subject to inductive forces are determined by the repulsion between the charges, which operates to produce the maximum separation. If the object is under the influence of outside charges, the charge locations are determined by the net effect of the inductive potential and the repulsion between like charges. In either case, the result is that the charges are confined to the outside surfaces of the conducting materials, and except for local variations in very irregular bodies, there are no charges in the interiors. And just remember, in Larson's system, static electricity is charged electrons that are charged. That's what he's talking about here. They go on the surface, the skin effect, whereas uncharged electrons are uncharged, and they constitute electric current. And electric current tends to move in matter, in the interior, the cross-section of the matter. So an electron, like everything in Larson's system, is a kind of motion, and an electron is a rotating unit of space. And like everything else in Larson's universe, a charge is also a kind of motion. It is a rotational vibration, which kind of looks like that. And a rotational vibration can attach to a an electron, to turn it from an uncharged electron to a charged electron. But a rotational vibration can also be applied to a subatomic particle or an atom. So when you charge or ionize an atom or subatomic particle, you're not putting an electron on it, you are putting a rotational vibration on it. Okay, so except for local variations in very irregular bodies, there are no charges in the interiors. The same considerations apply if the objects are hollow. The inside walls of such objects carry no charges. These walls may be charged by placing an insulated charged object in the hollow interior, but in that case, the inside walls are outside from the standpoint of the inducing charge. That is, they are the locations closest to that charge. The observed concentration of charge at the conductor surfaces is another direct contradiction of the accepted theory of the electric current, which views the current as a movement of charges. This concentration at the surface is due to the mutual repulsion between the charges, which drives them to opposite sides of the conductor. The repulsive force is not altered if the charges move along the conductor, since the direction of this force is perpendicular to the direction of movement. Nor would the presence of positive asterisk charges on the interior atoms of the conductor alter this situation if any such charges existed. And remember, Larson uses the asterisk after positive or negative because he finds that his positive is their negative in terms of the conventional scientists. So he's using the conventional terminology here when he says positive, but in his terminology, that would be negative. If the electrons, or any portion of them, are firmly held by the attraction of the hypothetical proton charges, then they cannot move as an electric current. If they are free to move in response to an electric potential gradient, then they are also free to move to the surfaces of the conductor under the influence of their mutual repulsions. From this, it follows that if present-day electric theory were correct, the current should flow only along the outer surfaces of the conductors. In fact, however, electric resistance is generally proportional to the cross-sectional area of the conductor, indicating that the motion takes place fairly uniformly throughout the entire cross-section. This adds one more item of evidence supporting the finding that the electric current is a movement of uncharged electrons, not of charges. Since no charges are induced within a hollow conductor by an outside charge, any object within a conducting enclosure is insulated against the effects of an electric charge. Similar elimination or reduction of these effects is accomplished by conductors of other shapes that are interposed between the charge and the objects under consideration. This is the process known as shielding, which has a wide variety of applications in electrical practice. Within the limits to which the present examination of electrical phenomena has been carried, there does not appear to be any major error in the conventional dimensional assignments, other than those discussed in the preceding pages. Aside from the errors that have been identified, the SI system is dimensionally consistent and consistent with the mechanical system of quantities. The space-time dimensions of the most commonly used electrical units are listed in Table 28. And, keep in mind that Larson's units go, different than SI system or the MKS system, Larson uses only units of space and time. All motions are relationships between space and time. They are all fractions with space or time as the numerator, time or space as the denominator. And they can be with multiple exponents. So the first column in this table lists the symbols that are used in this work. The other columns are self-explanatory. So he basically just has your basic units in this table 28, electric quantities. Time is T, the second. Also, we have dipole moment, the Coulomb, T over S. Now that is the fudge factor that Larson's using for his Coulomb. He's got the uppercase Coulomb and the lowercase Coulomb. One is T over S and one is just S. And I think that should have given Larson a clue that he was onto the wrong track here. But work, energy, the watt-hour, T over S. Charge, Coulomb, T over S. V, potential, the volt, T over S squared. Voltage, the volt, T over S squared. Electric field intensity, the volt per meter, T over S to the third. Flux density, the Coulomb, T over S, per meter squared, T over S to the third. Charge density, Coulomb per meter cubed, that's T over S to the fourth, which is also the units of pressure. Resistivity, the ohm meter, that's T squared over S squared. Resistance, the ohm, T squared over S to the third. Current density, the ampere per meter, 1 over ST, which is an unusual quantity in that it's not really a fraction, with space or time as the numerator and time or space as the denominator. Power is the watt, 1 over S. Displacement, the small case Coulomb, S, per meter squared, 1 over S. Polarization is also 1 over S, the Coulomb per meter squared. Space, the meter, S. Electric quantity, lowercase Coulomb, S. Capacitance, the farad, and he's also using S for that, but I believe that it is actually S to the third over T. We talked about that at length in the previous two chapters, I think, or at least the previous chapter on electrical storage. The current, or amperes, S over T. And permittivity, which is in farads per meter. And for some reason, Larson is using the correct units here, farads per meter, S squared over T, which means that the farad would be S to the third over T. It's right here. For some reason, he's using the right units for permittivity, which he derived from the wrong units for the farad. Don't get it. Anyway, conductivity, the Siemens per meter, S squared over T squared. And conductance, the Siemens, S to the third over T to the second. The natural units of most of these quantities can be derived from the natural units previously evaluated. Those of the remaining quantities can be calculated by the methods used in the previous determinations. But the evaluation is complicated by the fact that the measurement systems in current use are not internally consistent, and it is not possible to identify a constant numerical value that relates any one of these systems to the natural system of units, as was done for the mechanical quantities that involve the units of mass. In Larson's system, everything is quantized. There is the discrete unit postulate, and so all of his units, there can be a natural unit like 1. Like there is a natural unit of speed that is 1 unit of space over 1 unit of time, which turns out to be the speed of light. So the speed of light is unit speed. And then there is also unit pressure, unit mass, unit acceleration, unit charge, unit energy. And they're all, based on 1 unit, or 1 unit of space per 1 unit of time, or 1 unit of whatever t over s to whatever exponent over 1 unit of s over t exponent. Neither the SI system nor the CGS system of electrical units qualifies as a single measurement system in this sense. Both are combinations of systems. In the present discussion, we will distinguish the measurement systems as here identified by the numerical coefficients that apply in these systems to the natural unit of space, s, and inverse speed, t over s. On the basis of the values of the natural units of space and time in CGS terms established in Volume 1, the numerical coefficient of the natural unit of s, regardless of what name is applied to the quantity, should be 4.56 times 10 to the minus 6 centimeters, while that of the natural unit of t over s should be 3.33 times 10 to the minus 11, and that is in seconds per centimeter. In the mechanical system of measurement, the quantity s is identified in its most general character as space, and the unit has the appropriate numerical coefficient. But the concept of mass was introduced into the t over s quantity, here called energy, and an arbitrary mass unit was defined. This had the effect of modifying the numerical values of the natural units of energy and its derivative by a factor of 4.472 times 10 to the 7th, as was explained in Volume 1. The definition of the unit of charge by means of the Coulomb equation in the electrostatic system of measurement was originally intended as a means of fitting the electrical quantities into the mechanical measurement system. But as pointed out in Chapter 14, there is an error in the dimensional assignments in that equation, which introduces a deviation from the mechanical values. The electrostatic unit of charge and the other electric units that incorporate the ESU therefore constitute a separate system of measurement in which T over S is identified with electric charge. The unit of this quantity was evaluated from the Faraday constant in Chapter 9 as 4.80 times 10 to the minus 10 ESU. Unit charge can also be measured directly inasmuch as some physical entities are capable of taking more than 1 unit of electric charge. The charge of the electron, for instance, is 1 unit. Direct measurement of this charge is somewhat more difficult than the derivation of the natural unit from the Faraday constant, but the direct measurements are in reasonably good agreement with the indirectly derived value. In fact, as noted in Chapter 14, clarification of the small-scale factors that affect these phenomena will probably bring all values, including the one that we have derived theoretically, into agreement. An electromagnetic unit, EMU, analogous to the ESU, can be obtained by magnetic measurements, and this forms the basis of an electromagnetic system of measurement. The justification for using the EMU as a unit of electrical measurement is provided by the assumption that it is an electric unit derived from an electromagnetic process. We now find, however, this is in fact a magnetic unit. That is, it is a two-dimensional unit. It is therefore a unit of t squared over s squared, rather than a unit of t over s. To obtain an electric one-dimensional unit, t over s, corresponding to the ESU from the EMU, it is necessary to multiply the measured value of the EMU coefficient, 1.60 times 10 to the minus 20, by the natural unit of s over t, the speed of light, basically 3 times 10 to the 10th centimeters per second. This brings us back to the electrostatic unit, 4.80 times 10 to the minus 10 ESU. The electromagnetic system, in which an additional factor, meaningless in the electrical context, has been applied. I skipped a line there, sorry. The electromagnetic system is thus nothing more than the electrostatic system to which an additional factor, meaningless in the electrical context, has been applied. The SI system of units is a modification of the electromagnetic system. In the early days of electrical measurement, the ampere was selected as the fundamental unit, as was defined on an arbitrary basis, After more information had been accumulated, and the desirability of relating the measurement system to physical fundamentals was recognized, the electromagnetic EMU system was adapted for general use. But in order to avoid making a radical change in the size of the ampere, an arbitrary factor of 10 was introduced as capital M. As capital M. McCaig remarks, the appearance of such a number, quote, in a primary definition is unusual. It arises because although this definition is intended to fix the value of the ampere, we have already decided in advance fairly precisely the value we desire this unit to have, end quote. The arbitrary modification of the EMU values changed the numerical coefficient of the natural unit of t over s to 1.60 times 10 to the minus 19. Because of the lack of distinction between the electric charge, t over s, and electric quantity, s, in current practice, the same unit is used for both of these physical quantities in all three of the electrical measurement systems, as shown in Table 29. So Table 29 is called the numerical coefficients of the natural units. And we've got space-time, 4.56 times 10 to the minus 6, and 3.33 times 10 to the minus 11. Mechanical, the same, 4.56 times 10 to the minus 6 centimeters. And we've also got 1.49 times 10 to the minus 3 for the electrical, for T over S units. In the electrostatic, we're using 4.80 times 10 to the minus 10th for both. Electromagnetic, 1.60 times 10 to the minus 20th for both. SI modification, 1.60 times 10 to the minus 19 for both. In applying the principle of the equivalence of natural units to electrical quantities, it is necessary to take into account these differences between the numerical values applying to the different systems. For example, the natural unit of capacitance, the quantity that plays the principal role in the phenomena discussed in Chapter 15, is the natural unit of electric charge divided by the natural unit of voltage. T over S times S squared over T equals S. On the basis of the explanation of the natural electric units given in the preceding paragraphs, the value of the natural unit of electric charge in the CGS electrostatic system is 4.80 times 10 to the minus 10th ESU. The natural unit of capacitance, I completely lost my spot here. I am lost. The natural unit of capacitance in this is this value divided by the natural unit of voltage, which was evaluated in chapter 9 as 9.311 times 10 to the 6 volts, 10 to the 8th volts. The result is 5.15 times 10 to the minus 18 farads. As we found earlier, the farad is a unit of space, which I disagree with. I'm thinking that the farad is a unit of S3 over S to the third over T. That's not my derivation either. It's from a guy named Dave. The natural unit of space derived in volume 1 is 4.56 times 10 to the minus 6 centimeters. Dividing these two values, we obtain 1.13 times 10 to the minus 12 as the ratio of the numerical coefficients of the natural units. From geometric measurements, the centimeter as a unit of capacitance has been found equal to 1.11 times 10 to the minus 12 farads. The theoretical unit and experimental values are therefore in agreement within the limits of accuracy to which the present study of the electric relations has been carried. In this case, the application of the equivalence principle merely corroborates an experimental result. Its value as an investigative tool derives from the fact that it is equally applicable in situations where nothing is available from other sources. Okay, that is the end of the chapter. I have to say that all of Larson's juggling units and pushing around these numbers, I think is somewhat of a fudge factor. It works for him to kind of obscure for him the fact that he has some of these units wrong. But you can kind of juggle around the numbers and convince yourself that it's right. But I think the bottom line from just reviewing these chapters for me is that something smells fishy with some of these units, but in particular the farad. That we will be going over some of Bruce Perret's work later on that also takes a stab at correcting some of Larson's work in terms of the electrical system. So we're going to move on tomorrow to start chapter 17, which again is more on electrical units here, electrical phenomena called ionization. And I think that is the last chapter that we get into before we move into some of the magnetism stuff and some other stuff here. This book, I believe, has 27 chapters, so we still have like 11 chapters to go, but we're moving a little faster through it. And just recall that it's not as important that you learn the chemistry here. That's not really why we're focused on this. We're reading this because Larson's reciprocal system is a generalized system of everything. And so the same lessons that are taught in chemistry are going to be, it's going to be analogous to what you would learn in astronomy, or what you would learn in economics, or what you would learn in metaphysics, or what you would learn in religion, or astrophysics, or physics. So we're trying to learn the basic principles and the methodology that Larson uses to apply his reciprocal system so that you can apply it to whatever subject you'd like. Because again, the reciprocal system is a generalized system. It's a theory of everything. So, but you have to learn how it operates. So perhaps these examples here in terms of the electricity aren't very good examples to be instructive for learning the system, but we also kind of have to learn the mistakes that Larson made along the way, and maybe some proposals for how to correct those mistakes, but also how to avoid those mistakes. And I do think when Larson starts juggling these numbers around, he can get himself to convince himself that they are self-consistent when, I don't believe that they are in some applications. Okay, well, I think we'll call it quits here for today and move on to Chapter 17 on ionization tomorrow. So thanks for tuning in today,